3 times in recorded history, something has entered our solar system that didn't belong here. The first one vanished before we could study it. The second was too faint to analyze, but the third one didn't hide, and what it revealed rewrote everything. We go from the interstellar object that disappeared before anyone could explain it, to the one that arrived too dim to question, to the one that finally answered for all three. By the end, the vanishing act won't feel like a mystery anymore. It will feel like the first sign of a pattern. If you're the kind of person who'd rather understand deep space than just glance at it, hit subscribe. It helps us find more people who think the same way. We're genuinely glad you're here. Now, let's begin. Everything in our solar system belongs to the sun. Every planet, every moon, every fragment of ice and rock drifting in the dark between them, all of it is captured permanently in an orbit that curves back on itself. Some of these orbits take 8 months to complete. Some take 250 years, but they all return. That is the definition of belonging to a solar system. Whatever comes close enough to the sun is required by gravity to come back and do it again. There is only one way to break that rule. An object has to be moving so fast, on a path so extreme, that the sun's gravity cannot bend it into a loop. Instead of a circle or an ellipse, its path becomes something else, a hyperbola, a curve that bends once and then opens up forever. Astronomers measure this with a single number called eccentricity. Below 1, an orbit is bound, closed, repeating, permanent. Above 1, it is not bound at all. The object is simply passing through, on a trajectory that began outside the solar system and will end outside it too, with the sun acting as nothing more than a brief, one-time detour. For most of the history of astronomy, we assumed objects like this had to exist. Stars eject material all the time. Comets and asteroids get flung out of young planetary systems by close encounters with planets, sent drifting into the space between stars, sometimes for billions of years, before crossing paths with another star entirely at random. Do that enough times, across a galaxy with hundreds of billions of stars, and the numbers stop being small. One recent estimate puts the number of interstellar objects sweeping through the inner solar system at around 7 every year. A separate calculation suggests that within the orbit of Neptune alone, something like 10,000 of these objects could be present at any given moment. 10,000 visitors. And for most of recorded astronomy, the number we had actually caught looking was 0. Let's do the actual math on what bound and unbound mean, because the difference matters for everything that follows. Every object moving through the solar system has a certain amount of kinetic energy, energy of motion, and the sun's gravity is constantly trying to claw that energy back, pulling everything toward a closed, repeating path. If an object is moving slowly enough, gravity always wins eventually, and the result is an ellipse, a closed loop, returned to again and again for as long as the object exists. But if an object arrives already moving fast enough, faster than the sun's gravity can ever fully overcome, no matter how close the pass, the shape of the path itself changes character. It stops being a loop and becomes a hyperbola, a single curve, bent once by the sun's pull, that never closes. Cross that particular threshold, and no amount of additional time or distance will ever bring the object back. It is why an eccentricity of 1 on paper is such a small number and such a permanent verdict at the same time. Here is what that number is up against. Shrink the sun down to the size of a period at the end of this sentence. And the 10,000 interstellar objects estimated to be inside Neptune's orbit right now would be scattered across an area larger than a football stadium, each one a few thousand times smaller than that period, each one dark. Each one moving fast enough to blur across a camera sensor, before it can be properly focused and affect astronomers call trailing loss. Finding one isn't like finding a needle in a haystack. It's like finding one specific, unlit grain of sand somewhere across an entire stadium during the 1 week it happens to catch the light. That is why, for most of the history of telescopes pointed at the sky, this entire population remained purely theoretical. We knew mathematically that they had to be out there. We had no way to prove it. That is starting to change. A new facility, the Vera Rubin Observatory, high in the Chilean Andes, is built specifically to catch faint, fast-moving things that older surveys were built to ignore. Its camera is the largest digital camera ever constructed for astronomy, and its survey strategy, photographing enormous patches of sky over and over every few nights for 10 straight years, is designed exactly for objects like these, too faint to notice once, but impossible to miss once you're watching the same patch of sky change night after night for a decade. Researchers who have modeled what Rubin should find during that survey land on a wide range of estimates, anywhere from about 5 to 50 new interstellar objects over 10 years, depending on how many of them actually exist and how large they tend to be. Even the low end of that range would more than double everything we've ever learned about visitors from other stars. We are, quite possibly, standing at the very beginning of going from a catalog of 3 to a catalog of dozens. But that's a story still being written. For now, 3 is still the whole catalog. Then, in 2017, the number went from 0 to 1, 2 years later from 1 to 2, and in the summer of 2025 from 2 to 3, 3 confirmed interstellar objects. That is the entire catalog, across the whole of recorded astronomy. 3 visitors from other stars, other planetary systems, other corners of the galaxy that would otherwise remain permanently out of reach, because short of waiting for one of them to wander through. The only alternative is building something fast enough to chase down a target moving at tens of kilometers per second. We are not there yet, not close, but here is what makes the 3 we did catch so valuable. Each one revealed something the last one couldn't. The first one we almost missed entirely, and by the time we'd noticed, it was already most of the way out the door. The second one we caught earlier, but it turned out to be too faint, too distant, to tell us much beyond the basics. The third one is the reason we can finally look back at the first 2 and understand, for the first time, what we were actually looking at all along. This is the story of all 3, in the order they arrived, what each one revealed, what each one left unanswered, and how the third finally answered for all of them. Let's start with the one that got away. On the night of October 19, 2017, a postdoctoral researcher named Robert Wurick was reviewing images from the Pan-SDARRS-1 telescope on the summit of Haleakala on the island of Maui. Pan-SDARRS wasn't built to hunt for interstellar visitors. Its job was more routine: scan the sky night after night, compare image to image, and flag anything that moved, mostly near-Earth asteroids, the kind that might one day pose a real threat to Earth. That night, something in the data didn't match anything nearby. Wurick pulled up an image from the previous night and found the same faint streak, moving the same direction. Whatever it was fast, crossing more than 6 degrees of sky per day, far quicker than any ordinary asteroid at that distance has any business moving. Within days, astronomers around the world had turned their instruments toward it, racing to nail down its orbit before it faded from view entirely. And what they found didn't fit. The trajectory had an eccentricity of roughly 1, solidly, unambiguously hyperbolic. The object had entered the solar system from above the plane where the planets orbit, curved in tight around the sun at a distance closer than Mercury ever gets, and was now heading back out, never to return, not a comet on a 70-year loop. Not an asteroid on some long, elongated ellipse, something that had arrived from outside and was leaving for good. Astronomers gave it a formal designation, 1I 2017 U1. The I stood for Interstellar, a category that until that week had never needed to exist. Before the formal name was settled, the Discovery team briefly floated a different one, informally among themselves. Rama, after the mysterious alien spacecraft in Arthur C. Clarke's 1973 novel Rendezvous with Rama, a story in which astronomers first mistake an interstellar visitor for an ordinary asteroid, only to discover, after a much closer look, that it isn't one. The parallel wasn't lost on them. But a string of letters and numbers wasn't going to satisfy anyone for long, and working with Hawaiian language experts at the University of Hawaii at Hilo, the team settled on something else instead, ʻOumuamua. It roughly translates to a messenger from afar, arriving first, a scout. The name turned out to fit better than anyone could have predicted. It's worth pausing to appreciate exactly how narrow our window really was. Oumuamua had already made its closest pass by the Sun on September 9th. Swinging by at a distance closer than Mercury ever gets, and briefly reaching a top speed of nearly 88 kilometers per second, fast enough to cross the distance between New York and Los Angeles in about a minute. By the time Warwick spotted it, 40 days later, it was already well past that point and accelerating away. It crossed Earth's orbital distance in mid-October, missing our planet by a wide margin, and kept going. From the moment of discovery to the last usable observation, the entire scientific window, every telescope, every measurement, every paper this section of the video draws from fit inside about 3 months. That's the entire span of human contact with an object that had likely been traveling alone through the dark between stars for longer than our own species has existed. Word spread through the astronomical community within hours, and one of the largest coordinated observing efforts in recent memory followed almost immediately. The European Southern Observatory's very large telescope in Chile turned toward it. So did Gemini South and the Keck II telescope in Hawaii and the Canada, France, Hawaii telescope on the very same mountain where it had first been spotted. Everyone understood the same thing. Whatever this was, it was leaving, and there would not be a second chance. Spectra taken during that window showed a featureless, reddish surface, a color closely matching objects out in the Kuiper belt, the icy debris field beyond Neptune, rather than anything typical of near-Earth asteroids. It was one more small data point suggesting Oumuamua didn't cleanly resemble any single population we already knew. The first thing that stood out about Oumuamua was what it wasn't doing. Comets that swing this close to the Sun typically develop a coma, a faint, glowing envelope of gas and dust, released as surface ice warms and turns directly to vapor. Oumuamua showed nothing of the kind. Telescope after telescope searched for the faintest hint of a tail, a haze, anything. Nothing turned up. By every visual measure, it looked like a bare rock, an asteroid, not a comet, but its brightness told a stranger story. As Oumuamua tumbled through space, its light curve, the way its brightness rose and fell as different faces caught sunlight, swung by a factor of roughly 10 to 1. That is an extraordinary range for a natural object. Most asteroids are roughly potato-shaped, and their brightness barely shifts as they spin. To produce a swing like Oumuamua's, an object needs to be dramatically longer than it is wide, tumbling end over end on a period of roughly 7.5 hours, never settling into the smooth, single-axis spin most small bodies eventually fall into. Picture a surfboard or a cigar tumbling slowly end over end through the dark, catching sunlight unevenly with every rotation, brightening as its long face turns toward us, dimming almost to nothing as it edges sideways. Exact size estimates vary depending on assumptions about how reflective the surface actually is, but every model agrees on the shape, at least 6 times longer than it is wide, by some estimates closer to 10 times. Scale that up to something familiar. And the closest comparison would be a structure a couple of 100 meters long, roughly the length of 2 or 3 football fields laid end to end, but narrow enough at the other 2 dimensions to fit comfortably inside a single one of those fields. Nothing that elongated had ever been documented in our own solar system, before or since. Astronomers considered whether Oumuamua might actually be 2 smaller objects, loosely bound and slowly orbiting one another, a configuration that could also produce dramatic swings in brightness, as first one body and then the other catches the light. Careful modeling of the light curve made this possible, though not required. The data fit a single elongated body just as well as it fit a loosely bound pair. They also considered whether the extreme shape had formed that way from the start, or whether it was the result of something else entirely, solar heating stripping away a softer, more ordinary object, shedding material unevenly, until only a harder, elongated core survived the encounter. No single explanation fit cleanly enough to close the question. What was clear, across every version of the analysis, was that whatever Oumuamua actually was, it did not resemble a single catalogued object from our own solar system. None of that on its own would have made Oumuamua one of the most argued-over objects in modern astronomy. What did that was something researchers very nearly missed. As Oumuamua sped away from the sun, a team led by astronomer Marco Micheli tracked its position with extraordinary precision, feeding every available observation into an orbital model with 7 separate parameters, essentially asking the data, does this object's path match a world governed by gravity and gravity alone? For most solar system bodies, the answer is simply yes, and the analysis ends there. For Oumuamua, it didn't. The object was not where gravity alone said it should be. It was accelerating, gaining speed, very slightly, in a direction pointed away from the sun, fading in strength the farther out it traveled, in a pattern that tracked almost exactly with the inverse square of its distance. Let's put a number on very slightly. The added push came out to roughly 5 millionths of a meter per second, applied every second, about 2 million times weaker than the pull of Earth's gravity holding you in your seat right now. On its own, a force that small sounds almost irrelevant. But applied continuously, hour after hour, week after week, over the entire outbound leg of Oumuamua's journey, it was more than strong enough to show up clearly against the alternative, a purely gravitational path. The detection itself was overwhelming, on the order of 30 standard deviations above the noise in the data, the kind of statistical confidence that leaves essentially no room for coincidence. This wasn't a rounding error or a fluke of measurement. Something was genuinely pushing Oumuamua off the path gravity alone would have given it. For a comet, an inverse square acceleration pointed away from the sun has a well-understood explanation: outgassing. As ice on the sunward side sublimates, the escaping gas acts like a slow, continuous thruster, gently nudging the object's path. Solar system comets do this constantly. It's one of the most ordinary things a comet can do, except Oumuamua wasn't showing a single sign of it. No coma. No detectable gas, no measurable dust. NASA's Spitzer Space Telescope searched specifically for carbon dioxide, carbon monoxide, and fine dust, and came back with only strict upper limits, far too little to explain an acceleration this size through any ordinary cometary process. The object was behaving exactly like a comet in terms of its trajectory, while showing none of the physical evidence that makes a comet a comet. And here's where things get complicated. You can't really have it both ways. Either something is escaping from the object's surface and pushing it along, or nothing is. And if nothing is, something else entirely needs to explain a 30 sigma deviation from a purely gravitational path. Several research teams have tried to close that gap, and it's worth walking through what they proposed, because none of the explanations are frivolous, and none of them on their own has fully settled the question. One proposal, developed by astronomers Darrell Seligman and Gregory Laughlin, and refined further by later work, suggested the push could come from molecular hydrogen, not sitting exposed on the surface as ice where it would have boiled away long before Oumuamua ever reached the sun, but trapped deep within an ordinary body of water ice instead. The mechanism they proposed unfolds over an almost unimaginable span of time. Out in the cold of interstellar space, cosmic rays slowly bombard a body of water ice for millions or even billions of years, gradually breaking apart water molecules and leaving hydrogen gas trapped inside the ice matrix like air bubbles frozen into a glacier. Only when the object finally warms, on the one occasion in its entire existence that it happens to pass close to a star, does that trapped hydrogen find a way out, all at once, in a slow, sustained release. Hydrogen is so much lighter and more volatile than water that it could, in principle, escape in quantities too small to ever register as a visible coma, while still applying enough force to measurably shift the trajectory. It's an elegant idea, tying the acceleration to ordinary solar system chemistry rather than anything exotic, and it fit naturally into a growing picture of Oumuamua as an ancient, well-traveled fragment of comet. It also ran into technical pushback almost immediately, with other researchers working the physics through in more detail and arguing that trapped hydrogen released this way simply doesn't generate enough force to match what Micheli's team actually measured. A disagreement that, as of the most recent published exchanges on the subject, has never been fully settled either way. A separate team, Stephen Desch and Alan Jackson, proposed something else again, that Oumuamua wasn't a comet in any conventional sense at all, but a fragment of solid nitrogen ice, the kind of ice found today on the surface of Pluto, chipped off the surface of a similar Pluto-like world in some other star system, and later flung into interstellar space by a violent gravitational encounter. Perhaps a close pass by a large planet, perhaps something more catastrophic. Solid nitrogen sublimates efficiently and, crucially, unevenly, eroding faster on the side facing the sun than the side facing away. That asymmetry, they argued, could account for both the acceleration and the extreme flattened shape in a single stroke. An object slowly planed down, like a bar of soap worn thin under running water, by the very process that was also pushing it off course. It's a genuinely compelling idea for exactly that reason. It ties two separate mysteries to one cause. It also depends on nitrogen ice being far more common out among the planetesimals of other star systems than anything we've directly observed, and that assumption remains, at best, unconfirmed. And then there is the explanation that received, by far, the most public attention, the proposal from Harvard astrophysicist Avi Loeb, developed together with Shmuel Bialy. If nothing measurable was escaping from Oumuamua's surface, they argued, then perhaps the acceleration wasn't coming from outgassing at all. Perhaps it was coming from sunlight itself, pressing on an object thin enough for radiation pressure to matter. We don't notice sunlight pushing on anything here on Earth because everything around us is far too dense for the effect to register. But if Oumuamua were extraordinarily thin, closer to a sheet than a solid rock, Something closer to a few millimeters thick stretched across an area hundreds of meters wide. The pressure of sunlight alone could in principle produce exactly the kind of acceleration that was measured without a single molecule needing to escape from anywhere. Loeb went further, suggesting this profile was consistent with something like a light sail, a form of propulsion that does not require a natural origin. It's worth being precise about what was and wasn't actually being claimed. Loeb did not assert that Oumuamua was proven artificial. His argument was narrower, that the possibility couldn't be excluded by the available data, and that it deserved serious investigation rather than dismissal. Most of the astronomical community disagreed with how much weight the idea deserved, and continued to favor a natural, if still poorly understood, explanation over one requiring engineering. Even so, the Breakthrough Listen project pointed a radio telescope at Oumuamua anyway, scanning across a wide range of frequencies for anything resembling an artificial transmission. It found nothing. No signal, no structured pattern, just the ordinary radio hiss of an empty patch of sky. This is, in its own way, exactly how the field is supposed to work. An anomaly shows up. Multiple explanations get proposed, some more conventional than others. The unlikely ones get checked anyway, because ruling something out is still progress, and because the alternative, assuming an answer without testing it, is how bad science gets made. What almost never happens is a single, tidy explanation was arriving to close the case. That's not a failure of the process. It's what a genuinely new kind of object, examined for the first time with tools built for something else, tends to look like up close. So where did that leave things? With three competing, unresolved explanations, and no realistic way to test any of them further, because by the time this debate was fully underway, Oumuamua was already gone. The last usable observations came from the Hubble Space Telescope in January 2018, barely 3 months after discovery. After that, the object simply became too faint, too distant, and too fast to track. It is now somewhere beyond the orbit of Neptune, headed toward the constellation Pegasus, carrying its answer with it, permanently out of reach, unless something is eventually built fast enough to follow. That unless isn't purely rhetorical. A group of aerospace engineers connected to the Institute for Interstellar Studies looked seriously at whether a spacecraft could actually catch up to Oumuamua under a proposal known as Project Lyra. Their conclusion was that it might be possible using existing propulsion technology, but only through an extraordinarily aggressive maneuver, launching a probe on a trajectory that would first dive in toward the Sun using a close solar flyby to gain as much speed as possible from the Sun's own gravity before slingshotting back outward on an intercept course. Even in the most optimistic version of that plan, actually catching Oumuamua would take years, and it would require a launch far sooner than any agency has committed to. For now, the proposal remains exactly that, a proposal. The scout that arrived first is, for the foreseeable future, going to stay the one that got away. A scout arrived, revealed just enough to raise every possible question about itself, and then vanished before a single one of them could be properly settled. Here's a strange coda to the story, and it took years to come together. If Oumuamua's acceleration was so unusual, so hard to reconcile with anything in our own solar system, why would nature just happen to produce something like this, once, coincidentally, right as we developed the tools to notice it? It turns out nature didn't do it just once. Starting not long after Oumuamua's discovery, researchers going back through archival data began noticing something odd about a handful of ordinary near-Earth asteroids, objects that had been cataloged for years, that showed no visible coma, no tail, nothing that would mark them as anything other than bare rock. And yet their orbits, tracked carefully over time, didn't quite match a purely gravitational path either. They were drifting, very slightly, in ways that pointed toward the same kind of hidden, undetected outgassing suspected in Oumuamua. By 2023, researchers had formally identified enough of these objects to name the category dark comets, asteroids that behave like comets without ever looking like one. A year later, a follow-up study run by NASA-affiliated researchers doubled the known count to 14 and found they split cleanly into two distinct families: larger, more distant dark comets, and smaller ones that stay closer to the inner solar system. None of these 14 objects show an acceleration nearly as extreme as Oumuamua's. Its push remains, even now, an outlier by a wide margin, orders of magnitude stronger than anything measured in a dark comet, but their existence quietly reframes the entire debate. Whatever was happening to Oumuamua clearly wasn't some singular, one-off anomaly demanding an exotic explanation. It was an extreme example of a real, physical process, undetected outgassing on objects with little to no visible activity, that nature turns out to produce more often than anyone expected before 2017. Oumuamua didn't just raise a question, it quietly created an entire new field of study, one that's still active, still adding new members to its catalog, years after the object that started it all had already vanished from view. That doesn't fully resolve what Oumuamua was. It just tells us the mystery has company, and it's a useful reminder of how science actually tends to make progress on something this strange. Not with a single decisive experiment that settles everything at once, but with years of researchers going back through old data, asking whether an apparent one-off might actually belong to a pattern nobody had thought to look for yet. Oumuamua forced that search to happen. 14 quiet, unassuming asteroids turned out to be the result. That particular question, what actually pushes an object like this, when nothing about it seems to be visibly escaping, would not get resolved that year, or the year after, or for a long stretch of years after that. It sat there essentially as an open case file at the edge of astronomy, acknowledged, argued over, and completely unresolved. 2 years after Oumuamua disappeared, something else showed up, moving on a path that was, once again, unmistakably hyperbolic. This time, astronomers had more warning. This time we caught it earlier, while it was still approaching, instead of already halfway out the door. For a moment, it looked like we might finally get a second chance at an answer. We didn't, not fully. The second visitor turned out to be almost the opposite kind of problem from the first, not too strange to explain, but too faint to study in the kind of detail Oumuamua's mystery actually demanded. It confirmed some things. It left just as many questions standing. And it set up, without anyone fully realizing it at the time, exactly the conditions that would make the third visitor so extraordinary when it finally arrived. That's where we're headed next. 2 years after Oumuamua disappeared, something else showed up, moving on a path that was, once again, unmistakably hyperbolic. This time, though, almost nothing about the discovery matched the first one. Different kind of telescope, different kind of astronomer. Different kind of object entirely, in ways that would take scientists most of the following year to fully appreciate. If Oumuamua was the visitor that arrived, teased everyone with an impossible shape and an unexplained push, and vanished before a single question could be settled, the second visitor was going to be the opposite kind of story, not too strange to explain. Too far away and too faint to explain as much as everyone wanted. On the morning of August 30th, 2019, an engineer named Gennady Borisov was reviewing images from a telescope in Crimea, a 0-meter reflector that he had designed and built himself, at a private observatory he'd named MARGO, tucked into the hills near the village of Nochny. Borisov wasn't a professional astronomer. He maintained telescopes for a living at the Crimean astronomical station and hunted comets in his spare time, using instruments he built by hand, funded largely out of his own pocket, and by building custom telescopes on commission for other observatories. By the time this particular morning arrived, he had already discovered 8 comets this way, entirely on his own initiative, competing against professional all-sky surveys with budgets and staff he could never match. His method was, in its own way, almost old-fashioned: long nights of automated imaging, followed by hours of manually scanning the resulting frames by eye, looking for the one faint smudge of light that had moved against the fixed backdrop of stars. It's slow, repetitive work, the kind that automated detection software increasingly does faster and more reliably. Borisov kept doing it anyway. This 9th object was different from the start. Sitting low in the morning twilight, roughly 3 astronomical units from the sun, it showed a short, unmistakable dust tail and moved through the frame in a way that didn't quite match a typical asteroid. Borisov logged the coordinates, ran the standard hazard assessment every near-Earth object gets checked against. It came back rated as a potential concern, the kind of result that requires immediate reporting, and submitted it to the Minor Planet Center along with a note: "This looked diffuse." It looked like a comet, not an asteroid. Within days, the world's largest telescopes, including the 10-meter Gran Telescopio Canarias in the Canary Islands, and eventually the very same pan-STARRS system that had caught Oumuamua 2 years earlier, had turned to confirm what he'd found. It's worth remembering, too, that this wasn't beginner's luck. Borisov had spent years building and refining his own instruments specifically for this kind of search, working the same patch of sky repeatedly, developing an eye for the kind of faint, slow-moving smudge that a less experienced observer would dismiss as noise or a processing artifact. 8 previous comets bore his name already. This one just happened to be moving on a trajectory nothing else in the solar system could produce. The comparison people reached for almost immediately was Clyde Tombaugh, the amateur astronomer who discovered Pluto in 1930 using a telescope he'd built himself, before going on to a career in professional astronomy. Nearly 90 years later, another self-taught telescope builder, working alone, had just found something that had never been confirmed before in the entire history of the field: a second visitor from outside our solar system. There's something worth sitting with in that comparison. Oumuamua was found by pan-STARRS, a purpose-built, professionally funded, all-sky survey system, backed by a research university and designed from the ground up to catch exactly this kind of object. Borisov was found by one engineer, in his own backyard, using a telescope mirror he ground and polished himself, checking the results by eye because he didn't trust automated software to catch what a careful, practiced human glance still could. Both approaches found an interstellar object. Neither one has any obvious claim to being the correct way to do it. In a field increasingly dominated by enormous, automated, institutionally funded survey telescopes, Borisov's discovery stood as proof that a single, determined amateur, with the right equipment and the right patience, could still beat every professional system on Earth to one of the rarest finds in the history of the science. It wouldn't stay that way forever. Surveys like Rubin are, by design, going to make this kind of amateur discovery vanishingly rare going forward, but for one morning in August 2019, it did. Once the discovery was confirmed, the brightening began, slow and steady, exactly as predicted for an inbound object still weeks away from its closest approach. Around 16th magnitude in early October, already thousands of times too faint for the naked eye, but well within reach of research-grade telescopes. The comet continued to strengthen through November and into December, eventually peaking around magnitude 14. Near the turn of the year, just as it made its closest approach to both the Sun and Earth, that slow, predictable climb tracked continuously for months rather than glimpsed for weeks is exactly what gave researchers the luxury Oumuamua never afforded them: time to plan observations in advance. Request telescope time on a schedule rather than in an emergency scramble, and follow the same target night after night as it changed. The Minor Planet Center published a preliminary orbit within about 2 weeks, and by mid-September, the numbers left no real room for doubt. The object's eccentricity worked out to roughly 3, dramatically, almost absurdly more hyperbolic than Oumuamua's already decisive one. Let's put those two numbers side by side, because the difference matters. An eccentricity of exactly 1 describes a parabola, an object that arrives, loops once around the Sun, and departs in almost exactly the same direction it came from, deflected by a full 180 degrees. The closer an object's eccentricity sits to 1, the more sharply the Sun's gravity still manages to bend its path before letting go. The higher above 1 it climbs, the straighter and less affected that path becomes. Oumuamua's 1 sat much closer to that tightly bent boundary. Borisov's 3 sat much further out along the scale, its path deflected by only around 34 degrees on its way through the solar system, despite the Sun doing everything gravity could do to pull it in. It wasn't just unbound. It was defiantly, emphatically unbound, moving on a line so close to straight that the Sun barely registered as more than a brief detour. Of every hyperbolic comet ever recorded, and astronomers have logged thousands of weekly hyperbolic comets over the decades, kicked loose from the Oort cloud by a passing star or a planetary near-miss, drifting on orbits only barely over the boundary, none had ever approached an orbit this extreme. This one wasn't from the edge of our own solar system. It was from somewhere else entirely, and it wasn't subtle about it. Picture the two trajectories side by side, drawn out on paper. Oumuamua's path curves in sharply, wraps tightly around a point near the Sun, and curves back out again, a visitor that came in on something close to a hook shape, spending real time close enough for the Sun's gravity to leave an obvious mark on its route. Borisov's path, by comparison, looks almost like a straight line with the gentlest possible kink in it, as if it had barely noticed the Sun was there at all, nodded politely on the way past, and kept going. Same underlying physics, same star doing the pulling, and 2 visitors that responded to it in almost opposite ways, one held briefly and tightly, the other barely touched. There was one more piece of detective work that made the case even more solid. Researchers with the Zwicky Transient Facility, a wide-field survey based in California, went back through their own archived images and found the comet already present, faintly, in data going back to December 2018, more than 8 months before Borisov ever noticed it, when the object was still roughly 7 astronomical units from the Sun, far out past the orbit of Jupiter. Those pre-covery images extended the observed arc dramatically, and every additional data point only tightened the case for an interstellar origin. This wasn't a fluke of a short observing window. The object had been tracked, in hindsight, for the better part of a year before its discovery even happened. The IAU made it official on September 24, 2019, giving it the designation 2I Borisov, the second confirmed interstellar object, named for its discoverer, following the same naming convention used for every comet before it. Unlike Oumuamua's carefully chosen Hawaiian name, arrived at through consultation and translation, Borisov's name required no such process. Comet naming convention is older and simpler. The discoverer's name attaches to the object, permanently, the same way it has for centuries. Gennady Borisov, an engineer who built his own telescopes in his spare time, now shares a name with the second confirmed visitor from beyond our solar system, a distinction no amount of institutional funding could have purchased. Here is what made this discovery fundamentally different from the first one, in a way that mattered enormously for what came next. Oumuamua had already passed its closest approach to the Sun by the time anyone noticed it, discovered on its way out, with the clock already running out. Borisov was caught roughly 2 months before its perihelion, while it was still inbound, still brightening, still approaching. For the first time, the astronomical community wasn't racing to catch a visitor already halfway out the door. It had time to plan. And what that extra time revealed, almost immediately, was that this second visitor barely resembled the first one at all. Where Oumuamua showed no coma, no tail, nothing but a bare, tumbling, elongated shape, Borisov behaved exactly like an ordinary comet from the moment it was found. A visible coma, condensed and bright around the core. A dust tail that grew steadily as the comet approached the Sun, eventually stretching by one estimate from a team at Yale across a distance, roughly 14 times the width of Earth, a genuinely humbling scale for an object that, at its core, was probably only a kilometer or 2 across. Spectra taken early on, using some of the largest telescopes on the planet, matched the signature of a completely typical cometary nucleus. As David Jewett, the astronomer who led Hubble's observing campaign, put it at the time, Oumuamua had looked like a rock, while this one was genuinely active, and the fact that the two objects behaved so differently from each other was, in itself, a puzzle nobody had anticipated. Two visitors arriving 2 years apart, and neither one telling researchers anything close to what to expect from the next. Think about what that actually means, because it's easy to gloss over. These were, at the time, the only 2 interstellar objects ever confirmed. 2 data points out of a population that might number in the trillions across the galaxy. And instead of confirming some obvious, shared category, this is generally what visitors from other star systems look like. They landed on opposite ends of nearly every axis you could measure. One bare and elongated and mysteriously accelerating with no visible cause. The other a fluffy, icy, dust-shedding comet doing exactly what solar system comets do, just from somewhere else. If you'd only ever seen Oumuamua, you might have concluded interstellar objects tend to be small, rocky, and strange. If you'd only ever seen Borisov, you'd have concluded they're basically just comets, indistinguishable in behavior from the ones native to our own solar system. Both conclusions, drawn from a sample of exactly one, would have been wrong or at least dangerously incomplete. That tension between 2 visitors that agreed on almost nothing except their hyperbolic orbits is exactly the kind of thing that only gets resolved with a third data point, which is precisely why the third one, when it eventually arrived, would matter so much. With more warning time and a genuinely active coma to study, researchers had something Oumuamua never gave them: actual gas to analyze. 2 independent teams pursued the question in parallel, using very different instruments. One, led by Dennis Bodwitz at Auburn University, used the Hubble Space Telescope to observe the comet in ultraviolet light, light almost entirely blocked by Earth's atmosphere, meaning the observation was only possible from space. The other, led by Martin Cordner and Stephanie Millam at NASA's Goddard Space Flight Center, used the Atacama Large Millimeter/Submillimeter Array, a collection of radio dishes sitting at over 16,000 feet in the Chilean Andes, ideally suited to detecting the faint radio signature of cold gas. Both teams studied the comet during December 2019 and January 2020, right around its closest approach to the Sun, and both, working independently with completely different instruments, arrived at essentially the same conclusion. What they found was, in its own way, just as strange as anything about Oumuamua, if less immediately dramatic. Borisov's coma contained an enormous, almost startling amount of carbon monoxide, at least 173%, as abundant as water in the escaping gas, more than 3 times higher than any comet ever measured inside the inner solar system, within about 2.5 astronomical units of the Sun. The ratio of carbon to oxygen in its material came out nearly 6 times higher than anything seen in a solar system comet. That's not a small deviation from the norm. That's a fundamentally different chemical recipe. Here's why that matters, and it's worth walking through the logic carefully, because it's a good example of how much a single measurement can actually tell you. Carbon monoxide ice is extraordinarily volatile, far more so than water ice. It turns to gas at temperatures so cold that, in our own solar system, that transition doesn't happen until an object gets to roughly 11 billion miles from the Sun, more than twice Pluto's farthest possible distance. Water ice, by comparison, stays frozen solid until an object gets much closer in down around the distance of the asteroid belt. For Borisov to still be carrying this much carbon monoxide frozen and preserved, it had to have formed and then spent essentially its entire existence somewhere extremely cold, either very far out in its home system's own version of that deep, dim outer reach, or in orbit around a star cool enough that even a moderate distance would achieve the same effect, a red dwarf, for instance. The single most common type of star in the galaxy, dim enough that its habitable temperature zone sits much closer in than our own suns. Either way, the message was the same. Borisov came from a planetary system that built its comets out of different raw ingredients than our own solar system did, assembled under different conditions at different temperatures. In a protoplanetary disk that had simply ended up with more carbon relative to oxygen than the one the Sun assembled from 4.5 billion years ago. This was, in the most literal sense possible, a sample of another solar system's chemistry, the first time anyone had ever measured directly what the raw material of planet formation looks like somewhere other than here. Not a model, not an inference from starlight passing through a distant disk. An actual physical sample, drifting through our own solar system, releasing its own history into space where our instruments happen to be pointed at exactly the right moment. For all of that, Borisov never gave up everything researchers were hoping for, even with 2 extra months of warning. The comet never came especially close to either the Sun or the Earth, reaching perihelion at just over 2 astronomical units, more than twice the distance Oumuamua's tight, blistering pass had achieved, and never approaching Earth much closer than about 2 astronomical units either. At its very brightest, around the turn of the year, it still only reached roughly 14th to 15th magnitude, bright enough for large telescopes to study in detail, but thousands of times too faint for the naked eye or even most amateur equipment to ever pick out. That distance mattered in a very specific way. It meant the coma itself, the same cloud of gas and dust that made Borisov so obviously, reassuringly comet-like, also did the one thing Oumuamua's bare surface never did. It hid the nucleus. Estimates of the comet's actual size varied considerably depending on the method and the assumptions behind it, landing anywhere from under a kilometer to 2 or 3 kilometers across, embedded somewhere inside a glowing envelope of its own dust. Unlike Oumuamua, whose extreme, tumbling light curve gave researchers an unusually precise read on its shape and rotation, Borisov's nucleus was never directly resolved by any telescope, ever, at any point in its passage. We know an enormous amount about the gas it released, its chemistry, its trajectory back to within a fraction of a light-year of its likely path through the galaxy. We still don't know with any real precision what the solid object actually producing that gas looked like, its shape, its rotation, whether it was one coherent body or a loose agglomeration of smaller pieces held together by gravity and not much else. In this one particular respect, the second interstellar object gave us less than the first one did, not more. There's a broader lesson buried in that trade-off, one that would matter again later. A close, exposed pass, like Oumuamua's, gives you unmatched detail on shape and rotation, but risks missing the object's chemistry entirely if there's no coma to sample. A longer, more comfortable pass, like Borisov's, gives you all the chemistry you could ask for, but buries the underlying body inside its own emissions the whole time. Getting both on the same object would require something neither of the first two visitors provided, a target bright enough, active enough, and close enough for long enough to be studied on every front simultaneously. As of early 2020, nobody knew whether such an object would ever cross our path again, or whether the third interstellar visitor, whenever it eventually arrived, would repeat one of these two patterns, or invent an entirely new one. There was one more question researchers could finally attempt to answer with Borisov that Oumuamua's brief visit had never allowed. Where, specifically, had it come from? Working from the comet's precisely measured trajectory, helped enormously by that extra 8 months of pre-covery data pulled from the Zwicky Transient Facilities archives, one team of researchers ran the object's path backward through the galaxy. Using position and velocity data for millions of nearby stars gathered by the European Space Agency's Gaia mission, the idea was straightforward in principle, even if the computation was anything but if you know exactly how an object is moving now. And you know how every nearby star has been moving for the past several 100,000 years, you can calculate which star, if any, the object might have had a close encounter with in the past, a plausible point of origin. Or at least a plausible waypoint on its journey. The search turned up a candidate, a dim red dwarf star called Ross 573, which Borisov appeared to have passed within a small fraction of a light-year of, roughly 910,000 years ago, moving at a relative speed of about 23 kilometers per second. That's 9 times closer than the best candidate encounter ever identified for Oumuamua, whose own path, run through the same kind of analysis, never pointed convincingly back to any single nearby star at all. It's worth being careful about what a result like this does and doesn't establish. A close encounter nearly 1 million years ago doesn't prove Ross 573 is where Borisov actually formed. The comet could simply have been passing through that star's neighborhood on a longer journey that began somewhere else entirely ejected from its true home system by some earlier unrecorded gravitational event. Long before that encounter ever took place, what it does establish is a genuine waypoint, a real, calculable point of contact between this specific piece of another planetary system and a specific, catalogued star worked out with actual data rather than pure speculation. For Oumuamua, no comparable candidate has ever been found. For Borisov, at least, there is a name to attach to part of the journey, even if it isn't necessarily the whole story. It's a small reminder of just how much more Borisov gave researchers to work with, in nearly every category, except the one that mattered most for understanding what it actually looked like up close. Borisov had one more twist left before it faded from view for good. In March 2020, as the comet continued its outbound journey, astronomers using Hubble noticed something had changed in its appearance. Instead of the single, compact, bright core seen in every previous image, the nucleus now showed a second, smaller fragment, clearly separated from the main body, a piece that had broken away entirely, drifting slowly apart from its parent in the images that followed. Comet nuclei splitting apart isn't unheard of in our own solar system. The stress of solar heating, uneven outgassing, or simple structural weakness can crack a fragile, loosely bound body apart even without a dramatic collision. Solar system comets have done it before, sometimes dramatically, sometimes in full view of Earth-based telescopes. What made this different was who it was happening to. This was the only other confirmed interstellar object ever found coming apart in real time. In a way that added one more small piece to an emerging picture, whatever these visitors are built from, at least some of them, are held together loosely enough that the ordinary stress of a single pass by a star, heating unevenly, outgassing unevenly, expanding and contracting as different faces catch the light, can be enough to start pulling the whole structure apart. Borisov wasn't a single, monolithic rock, even outwardly disguised as one. It was more likely something closer to a loosely bound pile of ice and dust, barely holding its own shape together under its own gravity, doing what such bodies apparently do when a star finally gets close enough to test that structure. Follow-up observations continued through the following months, tracking both the main body and its detached fragment as the whole system faded, and eventually became too faint to usefully study somewhere around the middle of 2020, the last confirmed observations coming from Hubble in July of that year. Roughly 11 months after Borisov was first spotted from a backyard observatory in Crimea, it's now well on its outbound leg, heading toward the constellation Telescopium, never to return, carrying whatever remains of its structure back out into the dark it came from. So here is where the catalog stood for the better part of 5 years. 2 confirmed interstellar objects. One looked like a bare, tumbling, elongated rock, defied every attempt at a clean explanation for its motion, and vanished after roughly 3 usable months. The other looked and behaved exactly like a normal, if chemically unusual, comet, gave researchers a much longer observing window, and still managed to keep its own nucleus permanently hidden inside a cloud of its own making, before breaking apart entirely on its way out, between the two of them. Astronomers had learned an enormous amount, about shape, about chemistry, about how differently 2 objects from entirely separate planetary systems could turn out to look, and about how fragile these travelers can apparently be after however many millions or billions of years spent drifting alone between stars before we ever caught sight of them. What they hadn't learned was how to generalize any of it. 2 examples don't make a pattern. They make at best 2 boundaries on a range of possibilities that remained, in every meaningful sense, wide open. Was Oumuamua the strange one, or was it Borisov? Was either of them typical of anything at all, or were both simply the 2 most unusual members of a much larger, still entirely unseen population? There was no way to know. Not with a sample size of 2, and no realistic way to add a third, not without either extraordinary luck or a fundamentally better way of scanning the sky than anything that existed at the time. It's a strange position for a scientific field to sit in, honestly. 2 confirmed examples of an entire category of object, and neither one usable as a reliable baseline for the other. Every conclusion had to be held loosely, qualified, hedged against the very real possibility that the next visitor would break the pattern all over again, the same way Borisov had already broken whatever pattern a single data point like Oumuamua might have seemed to suggest. That second option was already quietly underway. Even as Borisov faded from view in 2020, construction continued high in the Chilean Andes on a telescope built explicitly to solve exactly this problem, to stop relying on luck, amateur persistence, and the occasional favorable trajectory, and start systematically searching the entire visible sky every few nights for anything moving too fast and too strangely to belong to the sun. It would be 5 more years before that telescope was ready. And when it finally was, it would end up playing a role in exactly the kind of discovery it had been built for, though not, as it turned out, by finding the object first. Then, in the summer of 2025, nearly 6 years after Borisov faded from view, something else crossed the threshold into our solar system. This one would not vanish after 3 usable months. This one would not spend its entire visible existence hiding its own nucleus inside a cloud of dust. This one would stay observable for the better part of a year, brought into range of nearly every major telescope on Earth and in space: Hubble, JWST, ALMA, Subaru. The newly operational Vera Rubin Observatory itself, at exactly the moment in history when those instruments were more capable, more numerous, and more coordinated than they had ever been. For the first time, the astronomical community wasn't going to be left choosing between 2 wildly different, barely comparable data points, forced to guess which one, if either, represented anything close to a typical interstellar visitor. It was about to get a third, watched more closely and for longer than the first 2 combined, and what that third visitor revealed wouldn't just add 1 more data point to the catalog. It would end up rewriting how researchers understood the other 2. That's where we're headed next. Then, in the summer of 2025, nearly 6 years after Borisov faded from view, something else crossed the threshold into our solar system. This time, everything about the discovery would be different. Not just from Oumuamua's frantic 3-month scramble after the fact, and not just from Borisov's 2-month head start before perihelion. This time, the astronomical community would get an entire season of warning. This time, the object wouldn't hide its nucleus, wouldn't vanish before the debate could be settled, and wouldn't leave researchers arguing over which of 2 wildly different data points actually represented anything typical. This is the visitor that didn't get away. There's a small, fitting coincidence buried in exactly how this third visitor was first caught. Months before its official discovery, the still new Vera Rubin Observatory, the same telescope introduced earlier in this story as the future of interstellar object hunting. The one under construction back when Borisov faded from view had already captured the object in its own early test images taken during the observatory's science validation phase well before anyone had formally announced anything. Nobody flagged it at the time. It took the Atlas survey's dedicated detection to actually trigger the alarm. But buried in Rubin's own archives was a preview of exactly the role that observatory is about to start playing on a much larger scale, quietly photographing interstellar visitors before the rest of the world even knows to look for them. On July 1, 2025, the Atlas Survey Telescope Asteroid Terrestrial Impact Last Alert System, a NASA-funded network built primarily to watch for objects that might threaten Earth, reported an object from its station in Rio Hurtado, Chile. It carried a provisional designation, A11PL3Z, before the astronomical community settled on something more memorable, 3I Atlas, the third confirmed interstellar object, named for the survey that found it, arriving, as best anyone could tell, from the direction of the constellation Sagittarius. At the moment of discovery, it was roughly 670 million kilometers away, sitting comfortably within the orbit of Jupiter, moving on a trajectory that, within days, left no ambiguity at all. Its eccentricity worked out to approximately 6. Let's set that number against the other two, because the progression is worth appreciating in full. Oumuamua came in at roughly 1, barely past the boundary between bound and unbound, its path still curving sharply around the sun. Borisov came in at 3. Dramatically straighter, barely bent at all. This third visitor blew past both of them, arriving on a trajectory nearly twice as extreme as Borisov's already record-setting path. Of the 3 confirmed interstellar objects in the whole of recorded astronomy, this one was, by a wide margin, moving the fastest and the straightest, the clearest, least ambiguous, most unmistakably interstellar trajectory anyone had ever measured. If Oumuamua barely qualified, and Borisov qualified emphatically, this one arrived looking almost insulted by the suggestion it could ever have belonged to our solar system in the first place. It was also caught extraordinarily early. Researchers went back through archival data from 3 separate Atlas stations around the world, plus the Zwicky transient facility, and pushed the observed timeline back even further, all the way to a faint detection by NASA's TESS spacecraft in early May, nearly 2 months before the official discovery. While the object was still too distant and too quiet for anyone to have flagged it as anything unusual, that's a genuinely remarkable piece of retrospective detective work, a spacecraft built to stare at other stars, watching for the tiny brightness dips caused by orbiting exoplanets, had unknowingly recorded a visitor from interstellar space passing through its field of view, and nobody realized it until months later, once they knew exactly where and when to look back. Oumuamua had been found on its way out, already past the sun. Borisov had been found roughly 2 months before its closest approach. This object was caught a full 4 months before its perihelion, expected around the end of October, the longest lead time by far that astronomers had ever had with an interstellar visitor. That lead time changed everything about what came next. Word of an object this promising spread through the astronomical community almost immediately, and what followed was not a scramble. It was a campaign, planned and coordinated in a way neither of the first 2 visitors had ever allowed. Observation proposals that would normally take months to review and schedule moved through the process in days. Telescope time that institutions guard jealously, allocated years in advance for other projects, got redirected on short notice, again and again, toward a single shared target. It's hard to overstate how unusual that kind of coordination actually is. Most of the time, competing research teams are fighting each other for a handful of nights on the world's best instruments. For a few months, starting in the second half of 2025, an enormous portion of that competition simply paused, in favor of everyone pointing roughly the same direction at once. Over the following months, Comet 3I Atlas was observed by essentially every major instrument we currently have pointed at the sky. The Hubble Space Telescope imaged it repeatedly, tracking its brightening coma as it approached the sun. The James Webb Space Telescope captured its first mid-infrared chemical fingerprint of an interstellar object, and later returned for a deeper look as the comet's activity increased. The European Southern Observatory's Very Large Telescope, and eventually its extremely large telescope under construction nearby, studied its composition in detail from the ground. The Atacama Large Millimeter Array, high in the Chilean Andes, listened to the faint radio signature of its escaping gas. The Subaru telescope in Hawaii caught it just after its closest solar approach, when its activity was at its peak. Gemini North and Gemini South both contributed early characterization. NASA's TESS, originally built to hunt for planets around other stars, had already caught it faintly before anyone knew to look. The SphereX Observatory measured the infrared glow of its dust and water, and organic molecules. Even spacecraft never designed with anything like this in mind got pulled into the effort. The Psyche mission, the JWST mission bound for Jupiter's icy moons, and Europa Clipper all found themselves, by sheer chance of trajectory, close enough to attempt their own observations. Mars orbiters watched it glow faintly in the Martian sky, the newly operational Vera Rubin Observatory. The very telescope built specifically to catch objects like this, the one whose construction was already quietly underway back when Borisov was fading from view in 2020, turned its enormous camera toward it as well. Capturing some of the sharpest images, yet of both the comet's coma and its hidden nucleus. No interstellar object had ever been observed by anything close to this many instruments, this thoroughly, for this long. For the first time, researchers weren't going to be forced to choose between studying an object's shape or studying its chemistry, the trade-off that had defined the entire story so far. With enough time and enough telescopes, they were finally positioned to do both, on the same target, simultaneously. Ground-based observations filled in details that would have been impossible with any single instrument. Spectroscopy from the Gran Telescopio, Canarias, one of the largest optical telescopes on Earth, measured the comet's reflected color precisely enough to place it as slightly redder than the D-type asteroids common in the outer solar system, with a spectral signature closer to the trans-Neptunian objects and centaurs that populate the icy fringes beyond Neptune than to either Oumuamua or Borisov specifically. The same observations pinned down a rotation period of roughly 16 hours and 47 minutes, a steady, unhurried tumble compared to Oumuamua's frantic 7.5-hour spin. As Martin Still, the NSF's program director for the International Gemini Observatory, put it at the time, the sensitivity and scheduling flexibility of facilities like Gemini North allowed for exactly the kind of rapid, early characterization that neither previous visitor had ever received this early in its passage. The first real complication showed up almost immediately, and it had nothing to do with chemistry. It was a much simpler, more basic question: how big is this thing? Early estimates, based on how bright the object appeared and reasonable assumptions about how much sunlight a typical icy surface reflects, suggested something startling. If the brightness were coming primarily from a solid, reflective nucleus, some calculations pointed toward a diameter as large as 20 kilometers, a scale that would make it roughly 100 times wider than Oumuamua's longest dimension, and tens of times larger than Borisov's core. Harvard astrophysicist Avi Loeb, working through the implied mass under that assumption, argued in a public blog post that an object this large showing up as only the third interstellar visitor ever detected represented a genuine statistical anomaly. If smaller objects like Oumuamua are common, he reasoned, we should have found tens of thousands of them before ever stumbling onto something this size. The claim spread quickly through science coverage. The third interstellar object wasn't just big, it was suspiciously, almost impossibly big, except sizing a comet is a famously difficult problem. And the reason is the same one that had already limited what researchers could learn about Borisov's nucleus 5 years earlier. A bright coma of gas and dust surrounds and obscures the solid body underneath, and separating the two from a distance using only reflected light requires assumptions that can shift the answer by an order of magnitude depending on what you assume about the surface. Loeb pushed the implied numbers further still in a separate analysis. If the object really were that large, its mass would come out somewhere above 33 billion tons, and by that estimate more massive than Oumuamua and Borisov combined by a factor of somewhere between 1,000 and 100,000. For context, That would still leave it smaller than the largest confirmed comet nucleus in our own solar system, a roughly 128-kilometer giant called Bernardinelli Bernstein, but coming from interstellar space rather than our own Oort cloud. A mass at that scale would have been strange precisely because of how rare something that large should statistically be if smaller objects like Oumuamua are genuinely common throughout the galaxy. As sharper data came in, the picture narrowed considerably. A detailed analysis of Hubble imaging from August 2025 bounded the nucleus to somewhere between 440 meters and 5 kilometers across, already a dramatically narrower and smaller range than the earliest headline-grabbing estimates. Later work incorporating a fuller picture of the coma's contribution to the total brightness brought the figure down further still, with recent published estimates converging on something closer to 1 kilometers across, comfortably larger than Borisov's compact core, but nowhere near the tens of kilometers scale that had briefly dominated the public conversation. Separately, researchers measuring the comet's actual dust output found it was shedding material at a rate of roughly 180 kilograms per second, at a distance of 2 astronomical units from the Sun, more than double the rate measured from Borisov at the same distance, evidence of an unusually active, productive surface even without needing an extreme size to explain it. This matters beyond just getting a number right. It's a clean, real-time example of exactly how this field is supposed to work, and exactly the distinction worth holding onto whenever a dramatic new claim shows up. A provocative, headline-ready number appeared early, built on a real but incomplete analysis, and rather than becoming the accepted answer, it got tested, narrowed, and substantially revised as better data arrived. The major anomaly framing didn't hold up. What replaced it was smaller, less dramatic, and considerably better supported. With the size question settling into a more modest, better supported range, the far more interesting results were coming from the chemistry. And this is where the third visitor finally started delivering on everything the first two had only partially offered. The European Southern Observatory's Very Large Telescope measured the ratios of carbon and nitrogen isotopes locked into the cyanide gas escaping from the comet's coma, a set of measurements essentially impossible to make on either Oumuamua, which never produced enough gas to sample, or in this specific way. On Borisov, these isotopic ratios function almost like a fingerprint of formation conditions, sensitive to the exact environment an object formed in and largely unchanged by however many billions of years it subsequently spent drifting through interstellar space, the same atoms in very nearly the same proportions that were present the day the object first condensed out of a disk of gas and dust around some other long-departed star. What the VLT team found was a set of ratios unlike anything measured in a solar system comet, a signature pointing toward formation in the outer reaches of an old low-metallicity star system, the kind of environment associated with some of the galaxy's oldest stellar populations. Stars that formed back when the Milky Way itself carried far less of the heavier elements it's accumulated since generation after generation of stars living, dying, and enriching the galaxy's chemistry a little further each time. Here's a way to picture what low metallicity actually means in practice. Every element heavier than hydrogen and helium, the carbon in your body, the oxygen you're breathing, the iron in your blood, the silicon in the ground beneath your feet, was forged inside a star at some point in the past, and scattered into space when that star eventually died. The very first generation of stars in the universe had none of this material to work with. They were built almost entirely out of the hydrogen and helium left over from the Big Bang itself. Each generation of stars after that inherited a little more of the heavier elements produced by the generation before it, and, in turn, produced a little more themselves. A low metallicity star, in this context, is simply a star that formed relatively early in that whole multi-generational process, before the galaxy had finished building up the rich chemical inventory that a star like the Sun, forming billions of years later, had freely available to it. A comet's isotopic ratios carry a faint echo of exactly how much of that inventory was around when its parent system came together. 3I Atlas's echo points a long way back. Working in parallel, a separate team using the Atacama Large Millimeter Array measured the abundance of deuterated water, a heavier form of water where one hydrogen atom has been replaced with deuterium, a hydrogen isotope carrying an extra neutron in the comet's coma. The result, deuterium levels more than 30 times higher than found in solar system comets, and more than 40 times higher than the concentration found in Earth's own oceans. Let's sit with that comparison for a second, because it's a genuinely strange one to picture. Every glass of water on this planet carries a specific, well-measured trace of deuterium built into it since the earliest days of the solar system. The water escaping from 3I Atlas carries roughly 40 times more of it. Since colder formation environments tend to preserve much higher deuterium ratios and warmer ones tend to erase them through chemical exchange, this was once again a signature of an object that formed and stayed. Extremely cold, likely in the distant outskirts of its parent system's protoplanetary disk, far from whatever star it originally orbited for the entire span of time before it was eventually flung loose. Then the James Webb Space Telescope weighed in with its own chemical fingerprint. Measuring the ratio of methane to water in the comet's escaping gas at roughly 11 times higher than any previously measured object in our own solar system, an extraordinarily large enrichment consistent with natural thermal processes acting on ancient chemically primitive ice. Rather than anything requiring an exotic or artificial explanation, meanwhile observations from the Subaru telescope taken just after the comet's closest approach to the Sun added a further layer. The ratio of carbon dioxide to water measured in the comet's interior turned out lower than earlier space telescope measurements of its surface had suggested, hinting that the outer layers, exposed for untold ages to cosmic radiation during the long interstellar crossing, may carry a different chemical history than the comet's less processed interior. Peel back the surface, in other words, and the ice underneath tells a slightly different story than the crust that formed on top of it. Put all three results together, the isotopes, the deuterium, the methane enrichment, and researchers arrived at an age estimate that would have sounded almost implausible attached to either of the first two visitors. 3I Atlas appears to have spent somewhere between 10 and 12 billion years drifting through the galaxy before it ever crossed paths with the Sun. For comparison, the Sun itself is about 4.5 billion years old. The Milky Way's oldest stars are thought to have formed within its first billion or 2 years of existence. This object was very likely already ancient, already adrift, already older than our entire solar system, quite possibly older than most of the stars visible in the night sky from anywhere on Earth at any hour before the Sun had even finished forming. There was one more twist worth including, because it kept the object from settling too neatly into any single category. As 3I Atlas passed through perihelion in late October 2025, and its activity peaked, its water production increased sharply. And follow-up observations from the Subaru telescope found its overall behavior shifting to look considerably more like an ordinary solar system comet, more like Borisov, in fact, than like the strange, quiet mystery it had first appeared to be from a distance. Post-perihelion data from JWST also picked up clear signatures of methane, methanol, and ethane, organic molecules, the same broad family of carbon-based compounds found throughout other comets, just in unusual proportions. It's worth pausing on that shift because it says something about how misleading a single snapshot of any of these objects can be. Early on, before perihelion, 3I Atlas looked ambiguous, active, but not dramatically so, its chemistry hinting at something unusual without yet showing its full hand. Researchers openly noted, at the time, that it didn't cleanly resemble either of its two predecessors, not the bare silence of Oumuamua, not the immediately obvious textbook activity of Borisov, only once it actually reached the sun. And the full heat of perihelion finally drove enough material off its surface to sample, properly, did the fuller picture emerge. An object that behaves under intense heating remarkably like a conventional comet, while still carrying a chemical memory locked into its isotopes and its ice. Of formation conditions unlike anything in our own solar system's history. This wasn't Oumuamua's bare, inexplicable silence, and it wasn't quite Borisov's straightforward familiarity either. It was something that, the closer it got to the sun and the harder researchers looked, kept revealing a little more of both, a reminder that typical and strange aren't fixed labels for an object like this. They depend entirely on how close you're looking and when. Given everything that had already been said publicly about Oumuamua, it was never realistic to expect this third object to avoid the same question. And once again, the most vocal proponent of taking that question seriously was Avi Loeb, who had already spent years arguing that Oumuamua's unexplained acceleration deserved more consideration as a possible technological signature than most of the field was willing to give it, with 3I Atlas drawing this much attention. This much genuine size uncertainty, and this many strange ancient chemical signatures, Loeb argued publicly, in interviews and in his own writing, that the unusual methane levels detected by JWST were worth asking whether they might indicate some kind of biological or artificial process, rather than assuming a purely natural one from the outset. In one televised interview, he framed the high methane readings as raising a genuine question about whether the comet's interior might harbor something more than inert chemistry, a possibility he was careful to frame as a question worth investigating rather than a conclusion. Consistent with the position he'd staked out on Oumuamua years earlier, the response from the broader research community was consistent and consistently skeptical. NASA and the wider astronomical community maintained based on the full weight of the chemical, orbital, and physical evidence gathered across dozens of instruments that 3I Atlas is a natural comet, full stop. Its unusual chemistry explained by ordinary, if extreme thermal outgassing processes acting on extraordinarily old ice, not by biology or engineering. The methane-to-water enrichment JWST measured, strange as the number sounds in isolation, fits comfortably within what models of ancient, highly processed cometary ice predict. Nothing about it required stepping outside conventional chemistry and physics to explain. And this time, unlike with Oumuamua, there was an actual dedicated search to point to, not just a proposal that a search should happen. Scientists with the SETI Institute used the Allen Telescope Array in Northern California to scan 3I Atlas across a wide range of radio frequencies. From 1 to 9 gigahertz, beginning within 24 hours of its discovery being announced, a genuinely rapid response made possible specifically because researchers now had months of advance warning rather than a scramble to react after the fact. Over more than 7 hours of observing time, they sifted through nearly 74 million individual radio signal candidates. After filtering out human-made interference and satellite noise, the ordinary background clutter of a planet full of radio transmitters, roughly 200 candidates remained for closer inspection. None of them showed any of the narrowband, structured signature that would indicate an artificial transmission. Nothing, just the same natural radio hiss that every other patch of empty sky produces. Once again, an unlikely hypothesis got proposed, got taken seriously enough to actually test, and got answered with data rather than dismissed on reputation alone. Once again, the answer that came back was a fully natural, if genuinely extraordinary, object. This is in a strange way the version of the story that deserves more attention than it usually gets, not the speculation itself, which draws headlines almost automatically, but the fact that the field has twice now built the actual infrastructure to test that speculation quickly and rigorously, and twice now. The natural explanation has held up completely. It's worth being fair to what Loeb's position actually is, too, rather than flattening it into a caricature. He has not claimed in either case that the evidence proves an artificial origin. His consistent argument is narrower and more procedural. That objects this unusual deserve the possibility to be checked explicitly and publicly, rather than assumed away by default. Judged purely on that narrower claim, the record over both Oumuamua and 3I Atlas arguably supports him. The checks did happen, and happened faster and more thoroughly, specifically, because the question had already been raised loudly enough that ignoring it wasn't an option. Where the field and Loeb diverge is over how much weight the unresolved parts of the picture deserve once those checks come back negative. That disagreement isn't likely to fully resolve after 3 data points. It may not resolve after 30. Step back from the chemistry for a moment and consider what this third visitor actually did that the first 2, individually, never could. Oumuamua gave researchers an incredible, precise read on shape and rotation, and almost nothing on chemistry, because it never produced enough gas to sample. Borisov gave researchers rich, detailed chemistry, and almost nothing on physical shape, because its own coma permanently hid the nucleus underneath. Recall the exact trade-off described at the end of Borisov's story. Getting both on the same object would require a target bright enough, active enough, and close enough for long enough to be studied on every front simultaneously. 3I Atlas, arriving with 4 months of lead time and drawing in literally every major instrument available to modern astronomy, finally was that target. It finally did both at once, measurable shape and size, however much that number moved around before settling, alongside the deepest chemical characterization any interstellar object has ever received. And what that combined picture revealed didn't just add a third entry to the catalog, it reframed the other 2. If a visitor from another star system can survive 10 or 12 billion years of drifting through the galaxy, older than the Sun, older than Earth, older than almost every star currently visible, before finally crossing our path, then Oumuamua's inexplicable acceleration and Borisov's exotic carbon-rich chemistry stop looking like 2 unrelated anomalies that happen to show up within 2 years of each other. They start looking like exactly what you'd expect from a tiny, essentially random sample of objects that could, in principle, be drawing from the entire multi-billion-year history of the galaxy, not just from nearby ordinary sun-like stars, but potentially from stellar populations that formed before our own galaxy had even finished assembling itself, some of which may no longer exist in any form at all. Think back, too, to the dark comets, that quiet population of ordinary near-Earth asteroids, discovered only because Oumuamua's strange behavior sent researchers looking for something like it closer to home. That discovery already suggested undetected outgassing on airless-looking bodies was a real, if subtle, physical process, more common than anyone had assumed before 2017. Now stack a genuinely ancient, chemically extreme, but entirely natural comet on top of that finding. The pattern holds. Every single time one of these objects has looked too strange to explain naturally patient methodical investigation, more data, more instruments, more time, has eventually produced a natural explanation, robust enough to satisfy the field, even when a full accounting of every detail like Oumuamua's exact acceleration mechanism still isn't completely settled. 3 visitors. 3 completely different stories on the surface, a bare, tumbling rock that defied easy explanation, an ordinary-looking comet with an extraordinary chemical signature, and a genuine relic, conservatively older than the sun itself, that finally arrived bright enough and early enough to be studied properly. And underneath all 3, the same quiet implication. The handful of interstellar objects sampled so far may not represent nearby star systems at all. They may be messages sent from a much deeper, much older part of the galaxy's history, arriving, entirely by chance, at exactly the moment we finally had the instruments ready to listen. That's the shape of the full picture. What's left is what it actually means for the 3 visitors individually, and for everything still waiting to be found behind them, the dozens or more, that Rubin and the surveys that follow it are now positioned to catch in the years immediately ahead, before going any further. It's worth taking a moment to actually sit with everything these 3 visitors have shown us, not as a list of facts to check off, but as one continuous story told in 3 very different voices. Each one only fully legible once you know how the other 2 turned out. It started with a scout that arrived already leaving. Oumuamua crossed into our solar system, swung past the sun closer than Mercury ever gets, and wasn't noticed until it was 40 days into its exit, a faint streak crawling across a routine asteroid-hunting image on a telescope in Hawaii. A postdoctoral researcher named Robert Wurick caught it almost by accident, comparing one night's data against the last, and within days, the world's largest telescopes had turned to follow a trajectory that made no sense for anything native to our own solar system. In the few months anyone had to look at it, it refused to behave like anything we'd catalogued before. No coma, no tail, nothing, but a bare tumbling, impossibly elongated shape brightening, and dimming by a factor of 10 as it spun end over end through the dark. On a rotation nobody could pin down to a single clean axis. Astronomers gave it a name that turned out to fit better than anyone expected, a messenger from afar, arriving first. And then, as if that shape alone weren't strange enough, it started drifting off the path gravity alone should have given it, nudged by some invisible hand that never showed itself in any coma, any gas, any dust that Spitzer or anything else could detect. 3 explanations arrived to try to account for it: trapped hydrogen, escaping slowly from ancient radiation-processed ice, a fragment of nitrogen chipped off some distant Pluto-like world, and in its most publicized form. The suggestion that sunlight itself might be pushing on something built too thin to be entirely natural, an idea taken seriously enough to prompt an actual radio search that came back with nothing but ordinary static. None of the 3 explanations fully closed the case. And the disagreement between them was never resolved before the object faded past the reach of Hubble in January of 2018, carrying its answer with it permanently out of reach, unless something is someday built fast enough to follow. A genuine engineering proposal exists for exactly that mission. And remains for now only a proposal. What Oumuamua left behind wasn't just an unsolved mystery, though. It was an entire new category of investigation. Researchers going back through years of ordinary near-Earth asteroid data, looking for anything else that might share Oumuamua's unexplained non-gravitational push, found it first in one object, then several, eventually 14. Dark comets, ordinary-looking asteroids hiding in our own solar system, betraying the same kind of hidden outgassing Oumuamua had first revealed, none of them nearly as extreme, but enough of them to prove the underlying physics was real, and not some singular, unrepeatable coincidence. The first interstellar object we ever found didn't just raise a question about itself. It quietly reshaped how an entire field looks at ordinary asteroids much closer to home. Then 2 years later, a very different kind of visitor showed up, found not by a professional survey, but by one engineer, alone in Crimea, scanning his own images by eye through a telescope he'd built with his own hands, competing against institutions with budgets he could never match. Where Oumuamua had shown nothing, Borisov showed everything a comet is supposed to show: a coma, a tail eventually stretching many times the width of Earth, a spectrum that matched ordinary cometary nuclei from the very first observation. Its orbit, at an eccentricity of 3, was more extreme than anything ever recorded for a solar system comet, and this time astronomers had 2 full months of warning before its closest approach, enough time to plan rather than scramble. For a moment, it looked like the answer to interstellar visitors might simply be their comets, like ours, just from somewhere else. Then the chemistry came back. Borisov's coma held carbon monoxide in quantities that dwarfed anything ever measured in a solar system comet, more than 3 times higher than any comet studied within the inner solar system, evidence of a body that formed and stayed somewhere far colder than anything in our own planetary history. Perhaps around a dim, common red dwarf star, perhaps in the deep outer reaches of a system built from different raw material entirely. Researchers even managed to trace its likely path back through the galaxy using the motions of millions of nearby stars. To a close encounter with a star called Ross 573 nearly a million years before it ever reached us, a real calculated waypoint on its journey, something Oumuamua's path never offered, and then in one final twist its nucleus split apart on the way out. Caught by Hubble in the act, a fragment drifting slowly away from the parent body, a reminder that whatever holds these travelers together, after however many eons spent drifting alone, can be fragile enough that a single pass by a star is sometimes all it takes to start pulling the structure apart. 2 visitors. 2 data points that agreed on almost nothing about shape, activity, or chemistry, and between them, no way to know which, if either, represented anything typical of what's actually out there. A bare rock that accelerated with no visible cause, and a fluffy, active, carbon-rich comet that hid its own nucleus for the entirety of its visible existence. Whatever the third interstellar object turned out to look like, it was never going to confirm a pattern the first 2 had already established, because the first 2 had never managed to agree on one. Then came the third. Discovered 4 months before its closest approach, the longest warning astronomers had ever had, stretching back further still to an accidental detection by a planet-hunting spacecraft that had no idea what it was looking at. 3I Atlas drew in nearly every major telescope currently operating. On Earth and in space, in a coordinated campaign that neither of the first 2 visitors had ever allowed. Its orbit was the most extreme of the 3 by a wide margin, an eccentricity of roughly 6. Barely bent at all by the sun's gravity, arriving and departing on a trajectory almost defiantly straight. Its size became a genuine public controversy, with early estimates suggesting something enormous, a major anomaly. In the words of the same astronomer who'd already spent years arguing Oumuamua deserved a second look, before more careful measurements incorporating a fuller accounting of the surrounding coma settled the question at a far more modest, far better supported figure. Closer to a kilometer across than to the tens of kilometers first floated, and then the chemistry arrived from 4 instruments working in parallel, each one measuring something the other visitors had never allowed anyone to measure at all. Isotopic ratios from the Very Large Telescope pointed to formation around an old, low-metallicity star system, the kind of environment associated with the galaxy's earliest stellar generations. Deuterium levels measured by the Atacama Large Millimeter Array came back dozens of times higher than found in our own solar system's comets or in Earth's oceans. A methane signature from the James Webb Space Telescope measured 11 times richer than anything previously recorded from any solar system object. Put together, the evidence pointed to an age of somewhere between 10 and 12 billion years, a visitor that had likely been drifting through the galaxy since before the sun itself finished forming, arriving entirely by chance. At the one moment in the history of our species when we finally had the instruments ready to properly listen, and even after all of that, as it swung through perihelion and warmed under direct sunlight for the first time in billions of years. It started behaving a little more like Borisov after all, releasing water, methane, methanol, and ethane in proportions that finally let it settle somewhere between the two extremes the first 2 visitors had staked out. It was checked for artificial signals, the same as Oumuamua had been, this time within a single day of its discovery being confirmed. Nearly 74 million candidate signals were sifted down to about 200 worth a closer look. Once again, nothing came back but the ordinary hiss of empty sky, 3 visitors, 3 completely different profiles on the surface. And underneath all 3, one shared thread. Each one, in its own way, forced researchers to build new tools, ask new questions, and reconsider assumptions that had seemed reasonable right up until the moment a piece of physical evidence arrived to test them. Oumuamua's mystery led to the discovery of dark comets closer to home. Borisov's chemistry gave us the first direct sample of another star system's raw material, and 3I Atlas arriving bright enough and early enough to be studied properly gave us the first real evidence that interstellar visitors might not just be nearby debris from ordinary sun-like stars. They might be messengers from the deepest, oldest parts of the galaxy's own history, arriving on schedules that have nothing to do with us. And everything to do with events that happened long before anything on Earth existed to notice. It's worth being honest about what 3 data points actually buys you, scientifically, because it's tempting to treat a pattern like this as more settled than it really is. 3 is still a small number. It's an enormous improvement over 2, which, as this video covered at length, gave researchers nothing but an unresolved contradiction to work with, but it's not yet the kind of sample size that lets anyone say with real confidence what a typical interstellar object looks like, or how common ancient pre-solar visitors like 3I Atlas actually are relative to younger, more ordinary ones. Statisticians have a healthy suspicion of drawing firm conclusions from a sample this small, and that suspicion applies here just as much as anywhere else. 3 ancient unusual objects could mean ancient objects are common, or it could just as easily mean we've had a run of unusual luck. And the 4th object, whenever it arrives, turns out to look completely ordinary by comparison. Both possibilities remain genuinely open. What 3 data points does buy you is a direction. A hint strong enough to take seriously that the population of objects drifting between stars is probably far more diverse and far older on average than anyone assumed back when Oumuamua was the only example anyone had ever seen. Confirming that hint, turning it into an actual, statistically meaningful picture of what's out there, is exactly the job the Vera Rubin Observatory was built for, and exactly why the small, quiet fact of its recent first light matters so much more than it might have seemed at the time. There's a specific kind of privilege buried in that timing, and it's worth sitting with for a moment before moving on. None of these three objects were sent. Nothing about Oumuamua, Borisov, or 3I Atlas was built, launched, or aimed. Whatever violent gravitational encounter, billions of years ago, flung each of them loose from wherever they formed, did so with no destination in mind and no awareness that a destination even existed. They have been drifting, essentially at random, through the vast, mostly empty space between stars for millions of years in Oumuamua's case, for the better part of the age of the universe in 3I Atlases. Their paths through our solar system were not appointments. They were the astronomical equivalent of weather, inevitable in aggregate across a large enough galaxy and a long enough time, but utterly indifferent to who, if anyone, happened to be standing in the way when they passed. Try to picture 10 to 12 billion years the way you'd picture a distance instead of a duration, because as a plain number, it stops meaning very much after a while. If you compress the entire history of the universe, everything from the first moments after the Big Bang to right now, into a single calendar year, the Sun and the rest of our solar system wouldn't begin forming until early September. Earth would firm up as a planet a few days after that. The first simple life would appear sometime in mid-September. Every human being who has ever lived, every war, every civilization, every book, every telescope ever built, would be compressed into the final few seconds before midnight on December 31st. 3I Atlas on that same calendar was already adrift and traveling before the year had barely started, sometime in January or February, long before the sun was anything more than a cloud of collapsing gas. It spent the entire rest of that calendar year in transit, through spring through summer. Through the sun's formation, through Earth's formation, through billions of years of life, slowly complicating itself into the kind of creatures capable of building a radio telescope. And it happened to complete its journey and cross our solar system in the last few days of December. At almost exactly the same moment, those creatures finished building the instruments that could actually see it arrive. Put another way, if the whole story of the universe were a single page, everything covered across these four parts, the discoveries, the telescopes, the isotopes, the arguments about size and chemistry and possible technosignatures, would fit inside the very last letter of the very last word. Everything that has ever mattered to us happened there, in that final letter. The comet spent the entire rest of the page getting to us. And yet, despite that timing, somewhere in the last decade of that multi-billion-year journey, each of these three ancient wanderers crossed paths with a small, wet planet that happened, at that exact moment, to be occupied by a species that had only just finished building the tools capable of noticing. Move Oumuamua's arrival back 100 years, and it passes through an empty solar system, unnoticed and unremarked, exactly as every other interstellar object before it had done for the entire prior history of Earth. Move it forward 100 years, and by then it might have been one interstellar object among dozens already catalogued, a curiosity rather than a genuine, field-defining surprise. It arrived instead in the precise, narrow window when a global network of survey telescopes had just become sensitive enough to catch something that faint and that fast, but before the population had become familiar enough to stop making headlines. The same is true even more sharply of 3I Atlas. An object that spent 10 or 12 billion years in transit happened to complete that journey during the specific few years when the James Webb Space Telescope, the Vera Rubin Observatory, and a coordinated global observing network all existed simultaneously ready to receive it. That's not a message in any meaningful sense. Nothing about these objects was trying to reach us any more than a raindrop is trying to reach a specific blade of grass, but it's very difficult not to experience it as one anyway. A wanderer older than the sun crosses the one habitable rocky planet in the galaxy at the one moment in that planet's history when something on it had finally built eyes sharp enough to see it clearly, and then it keeps going forever. Indifferent to the fact that it was ever seen at all, we didn't receive a message. We happened to be standing somewhere with the right instruments at the right time to intercept a piece of evidence that was never addressed to anyone, and chose, because that's what we do, to read meaning into it anyway. It's worth noticing the asymmetry here, because it cuts both ways. We have ourselves sent things outward with actual intention attached. The Voyager probes launched in the 1970s carry golden records, recordings of Earth sounds greetings in dozens of languages, an attempt, however modest and however unlikely, to ever be found to put a genuine message into interstellar space. Aimed at nobody in particular in case somebody happens to be listening someday. Oumuamua will overtake Voyager, one's current distance from the Sun sometime around 2038. Two objects moving outward past each other on their way to entirely different destinations, one carrying a message nobody sent. The other carrying a message we deliberately wrote and have no way of knowing will ever be read. It's an odd kind of symmetry. Our species' one confirmed attempt to send something meaningful into the dark, passed, almost in the same breath, by three separate examples of what meaningless actually looks like when it's the default. The interstellar objects we caught weren't trying to say anything. The tiny, deliberate message we sent out ourselves might never be received by anyone capable of understanding it either. Both situations amount to roughly the same thing from far enough away, a small, brief signal sent or received almost entirely by accident into a silence too large to measure. Whether that silence stays permanent or whether it eventually gets broken from either direction isn't a question any of these three visitors could answer. It's simply the question they leave behind once everything else about them has been measured as thoroughly as current instruments allow. There's an old idea in astronomy, worn nearly smooth from repetition by now that we are the universe's way of observing itself, that the atoms making up a human brain were forged in stars scattered across the galaxy, and eventually assembled into something complex enough to look back up and wonder where it all came from. These three visitors sharpen that idea into something more specific and, if anything, stranger. It isn't only that we are made of the same material the universe is made of. It's that occasionally, rarely, by the plainest kind of cosmic coincidence, a fragment of that same universe's much older history drifts directly through the small patch of space we currently occupy. At the precise moment we're capable of turning around and actually looking at it. 10 billion years of galactic history compressed into a comet, the length of a few football fields, passing within telescope range of a species that had by pure accident of timing just finished building the equipment to say hello back, even knowing the entire time that nothing on the other end was listening for a reply. Every planet, every star, every galaxy we've ever studied has taught us something about processes, how stars form, how gravity works, how chemistry unfolds across unimaginable timescales. These three objects taught us something slightly different and slightly more personal, if a comet can be said to teach anything personal at all. They taught us about arrival, about what it means to be in a specific place, at a specific and unrepeatable moment, when something ancient and indifferent happens to pass close enough to notice. Oumuamua will never be intercepted. Borisov is already breaking apart somewhere past the orbit it once crossed. 3I Atlas is receding back toward whatever remains of the deep, dark stretch of the galaxy it spent 10 billion years traversing before we ever knew it existed. None of them are coming back. None of them were ever going to. There's a version of this that applies closer to home, too. Earth itself is not so different from these visitors, in one specific sense. It is a single, finite vessel, carrying everything it needs to sustain what's aboard it, moving through a mostly empty universe on a trajectory shaped by forces well beyond anyone's control. The comparison usually gets made to emphasize fragility, and that's fair. A closed system only works for as long as its systems keep working, but these three visitors add a different angle to it. A ship traveling alone for 10 billion years, fragile enough that a single close pass by a star can crack its structure apart, still made it. Still crossed an entire galaxy's worth of empty space, still arrived intact enough to be measured, sampled, and understood, if only in fragments, by whoever happened to be watching when it finally passed close enough to see. Fragility and endurance aren't opposites here. They're the same fact, looked at from two different distances, but we were there. For one narrow window, measured in months rather than years, 3 times now, we were exactly where we needed to be, with exactly the tools we needed to have to catch a fragment of a much older story passing through. That's not nothing. In a universe this large, and a galaxy this old, being in the right place at the right time, even once, is already a kind of improbability worth pausing on. Being there 3 times in less than a decade, at the exact moment our own instruments finally caught up to the scale of what's actually out there passing by, that starts to feel less like coincidence and more like the leading edge of something much bigger, only just beginning. Consider, too, what these 3 visitors imply about everything we haven't caught. If 7 interstellar objects really do pass through the inner solar system every year, and we've only ever confirmed 3 across the entire span of recorded astronomy, then the overwhelming majority of this population has been drifting past us unnoticed and unrecorded for as long as anyone has been capable of watching the sky at all. Every one of those uncaught visitors carried the same kind of ancient, unrepeatable story that Oumuamua Borisov and 3I Atlas happened to reveal, a fragment of some other star system's history, a sample of formation conditions nobody on Earth has ever directly measured gone forever unread, simply because nobody happened to be looking at the right patch of sky on the right night with the right instrument. That's not a failure. It's just the ordinary cost of trying to observe a universe this vast with tools that, for nearly the entire history of astronomy, were nowhere close to sensitive enough for the job. What's changed only very recently is the sensitivity of those tools, and with it, the odds that the next ancient wanderer won't simply pass by unnoticed the way most of its predecessors did. 3 times in recorded history, something has entered our solar system that didn't belong here. We know that now in far more detail than we did at the start of this. The first one vanished before we could study it properly, but not before its strangeness quietly rewrote what we thought we knew about the objects hiding in our own solar system's shadows. The second one didn't hide. It behaved exactly the way a comet should, right up until its chemistry revealed a birthplace colder and stranger than anything the sun ever produced. And the third one didn't just avoid hiding. It stayed long enough and arrived bright enough for nearly every instrument we have to finally get a proper look, and what it showed us was older than the star we orbit. 3 visitors, 3 stories that on their own could each pass as a strange but isolated curiosity. Put together in order, they tell something larger, that the galaxy is far older, far stranger, and far more generous with its evidence than a single data point could ever have suggested. 2 objects looked like an unresolved contradiction. 3 started to look like the beginning of a pattern, and the Vera Rubin Observatory, already quietly working through its first years of operation, is positioned to turn that beginning into something approaching a real census, one interstellar visitor at a time, for the next decade. Somewhere between 5 and 50 more of these are expected before that survey ends. Some of them may resemble Oumuamua, some may resemble Borisov. Given what 3i Atlas just showed us about how old and how varied these travelers can actually be, it's just as likely the next one resembles neither and teaches us something none of the first 3 managed to reveal on their own. We didn't summon any of them. We didn't send anything out to greet them, and nothing about their arrival had anything to do with us. But we were watching, at exactly the right moment, 3 separate times, and we understood a little more of the galaxy's own deep history each time because of it. That's the quiet promise sitting underneath everything the Rubin Observatory is about to start doing. Not a message exactly, but an ongoing invitation to keep watching precisely because something worth seeing keeps arriving. On a schedule that has nothing to do with us and everything to do with what's actually out there. There's something worth carrying with you from all 3 of these stories, beyond the specific chemistry, the specific numbers, the specific instruments involved. It's this: the universe doesn't owe anyone a front row seat to its own history. Most of what happens unwitnessed, in the dark, across timescales too long for anyone to be watching at the right moment. And then, every once in a rare while, for no reason connected to merit or effort or anything except plain, blind timing, something ancient wanders directly into view at the exact moment somebody happens to be looking up. 3 times in less than a decade that somebody was us. Not because we were owed it, not because these fragments were meant for us in any sense that would hold up to scrutiny. Simply because, after a very long stretch of not having the tools to notice, we finally built some that did, and the galaxy, indifferent as it is to who's watching, kept sending material through regardless, waiting for nobody in particular to finally be ready. If a story like this one pulls at you, the idea that a fragment of another star system older than our own could quietly cross our path and be gone again before most of us ever heard about it, there's a related question sitting right behind it. One we haven't tackled yet. If planetary systems really are this common and material really does drift between them this freely, then where is everyone? That's the Fermi paradox, and it's next. Until then, the sky keeps doing what it's always done. Something else is out there right now, already on its way, following a path it's been tracing since long before any of this existed to notice. We just have to keep looking.